Okay, what we're going to do today is look at 8.2, which is a section that deals with graphing simple rational functions. Some of these rational functions can just be super, super challenging, but we're going to look at some of the simpler versions. And a rational function is anything that looks like a fraction, where you have variables in the numerator and the denominator. And along those lines, the denominator cannot be equal to 0. So your rational functions are going to have this shape right here, okay, where you've got one function over another, and the really important piece of this info is that bottom function cannot be equal to 0. Okay, so I've got for you the graph of the function 1 over x. X is in the denominator. And so this is what's called a hyperbola. We're going to talk about that later. And it consists of two symmetrical parts that are called branches, and those are the purple lines. All right. The domain and the range are all non-zero real numbers. So when you look at this guy, what you've got is a vertical asymptote on the y-axis and a horizontal asymptote on the x. And these asymptotes, let me see here if I can move this guy up just a little bit. These asymptotes are not included in the domain and range because there's no way that we can put a 0 into the denominator of this function and get an answer. So when x is 0, that number cannot be used, okay, because it's just not in the domain. So any function of the form g of x equals a of x, which is what this g of x equals a of x, which is what we've graphed, okay, has the same asymptotes, domain, range as the function 1 over x. So if you were to graph, if we were to look at a simpler function like, say, h of x equals 4 over x. Well, this is the exact same asymptote, domain, and range as 1 over x. So we're going to have asymptotes at x equals 0, asymptotes at y equals 0. The domain is going to go from negative infinity to 0, but 0 is not included, together with 0 to infinity, but 0 is not included. The range is going to go from negative infinity to 0, 0 is not included, and then go from 0 to infinity. And again, 0 is not included. So this is the setup for a rational function and their graphs. Okay, so let's graph the function y equals 6 over x and compare it to the parent function y equals 1 over x. And again, like we just saw in the previous slide, if we're looking at y equals 1 over x, we have some vertical and horizontal asymptotes on the x and y axis. Like, we know that for a fact. Okay? And then what we can do is just make a t-chart of points, and we can look at both. So let's just really investigate this guy right here. Don't need that. Let's investigate this guy right here. Y equals 1 over x. So what we'll do is we'll pick some points, some x coordinates, and we'll find some y coordinates. So let's look at, like, say, negative 2. I'll tell you what. Let's look at negative 3. Let's look at negative 3, negative 2, and 1. We can't look at 0. So then let's look at 1, 2, and 3. And so when I put a negative 3 in for x, I get negative 1/3. And when I put negative 2 in for x, I get negative 1/2. And when I put negative 1 in for x, I get negative 1. And then I get 1, 1/2, and 1/3. So when I graph this guy, I'm going to have the point negative 1, 1. I'm going to have the point negative 2 and a half. I'm going to have the point negative 3 and a third. And notice that this is going to also curve up and follow along with the x-axis, and those are all on the wrong side. So let me fix that. So these guys are in the wrong spot. There we go. Okay, so what I'm going to have is a graph that goes through these points and curves up along this axis. So it's going to look something like this. This is our parent function. So I get the same numbers going this way. Oof, not very pretty, but doable. All right, and these graphs do not cross the x and y axis. Okay, so now when I look at, say y equals 1 over equals 6x 6 over x, I can do the same things. So I've got x and y here, and let's just pick the exact same points: -3, -2, -1, 1, 2, and 3. And so when I put -3 in for x, I get -6 over 3, which is -2. And when I put -2 in for x, I get -6 over 2, which is -3. And then when I put -1 in for x, I get -6 over 1, which is -6. So when I look at this half at -3, I'm at -2. At -2, I'm at -3. And at -1, I'm at -6. So what this has done is it's going to have the same curve as the previous guy, but it's stretched out a little bit further. Okay. Well, when I put 1 in for x, I get 6 over 1, which is 6. When I put 2 in, I get 6 over 2, which is 3. And when I put 3 in, I get 6 over 3, which is 2. So again, at 1, I'm at 6. At 2, I'm at 3. And at 3, I'm at 2. So this guy is going to curve and look a little like this. All right. So what's the difference? Well, the difference is we're a little bit further away from the origin, but we still have the same shape. There's still two branches, and they are still have to stay within the restriction of they cannot cross the x-axis or the y-axis. So if we look at the domain for the blue function, it's just like the black function. It's going to go from -infinity to 0, and from 0 to infinity. Remember, these are your x numbers. The range are your y numbers, and they go from -infinity to 0, and from 0 to infinity. And I have a horizontal asymptote when y equals 0, and I have a vertical asymptote when x equals 0. And all of that is exactly like the parent function. Okay, so not every single function is going to have the shape y equals 1 over x, and that's why math, is because not everything is always that's quite that simple. But when you're graphing these rational expressions, if they're given to you in the shape that's shown here with y equals a over x minus h plus k, what they're giving us are the translation to the right, and they're giving us the translation up for our asymptotes. And then we draw the graph 1 over x according to where these asymptotes have put us. So to graph these, what you do is x minus h, remember, it's super secret opposite society when you're working on that x part. So when they give us that h value right there, minus h, that is our asymptote. So look down here in this problem, y equals 3 over x minus 4 plus 2. And down there in the bottom, we've got minus 4 right here. That means that we're going to have a vertical asymptote at the x-coordinate 4. So a vertical asymptote goes up and down like this. And notice that this graph curves right around that asymptote. Okay, the purple lines don't cross it. The next thing that we need to look for is the horizontal asymptote, and that's the number on the end all by itself. And if it's a number, that's where your asymptote is. If there's no number, your asymptote will be the x-axis. And so that guy goes right there. And if you'll notice, compared to the graphs that we have just been working on, we have got y over 1 over x. Y equals 1 over x. Okay. And then what we can do is we can just pick some points out of this and graph them if we want. And we want to graph them based on the horizontal and vertical asymptotes. So for this particular guy, what I would do when I pick my x and y points, if I've got x and y, what I would do when I would pick my points is I would put that 4 in the middle. So I would pick 1, 2, and 3. And then up 4, I'm undefined. So then I'm going to pick 5, 6, and 7. And if I'm picking my x value, then I'm going to find my matching y value. So to set up the old-fashioned t-chart, y is equal to 3 over x minus 4 plus 2. So what's that going to look like? Well, it's going to look like 3 over 1 minus 4 plus 2. And you can do this math, either on a calculator or by hand or whatever. But 3 divided by negative 3 is negative 1, and negative 1 plus 2 is 1. And then I take the same step again here with 2. So I'm going to have 3 over 2 minus 4 plus 2. And that's going to end up being negative 3 halves plus 2. And so again, you can punch it into your calculator or do it by hand, but negative 3 halves plus 2 is going to be a half. And then do the same thing for 3. So you're going to do the same thing for all these points right here. And you just fill in the x value for x and get your matching y. So this is the coordinate 1, 1, just like when you were first making your very first line charts, t-charts forever ago. Okay? And so we just plot all these points and you get this purple line right here. So notice though it has the exact same shape as 1 over x. And that's the key thing. All these shapes are going to be the same. Okay, so what if you get a rational expression that's given to you with everything in one big fraction? Well, now that gets a little bit more tricky to solve out. But it's still doable. It will still give you that same parent function that we've been dealing with for this entire section. So if I'm going to graph this guy, I still am going to have something that looks like this, okay? But I have to do a little bit of math to find that thing. So the vertical asymptote of the graph is the line x equals the opposite of d over c. Okay? Because what we're saying is x minus 3, when that equals 0, we're undefined. Why? Because in the denominator, down here in the denominator, the thing that you cannot have in the denominator is the number 0. Okay, it's undefined when you have a 0 down there. So if you set the denominator equal to 0, then you can figure out what your horizontal asymptote is, or your vertical asymptote. And in this case, our vertical asymptote is at 3. So I can go ahead and draw that guy in, drawing my vertical asymptote. Alright, once we've got the vertical asymptote, we can find the horizontal asymptote. And the horizontal asymptote is the ratio of the numbers in front of the x's. And so for this particular guy, our horizontal asymptote is going to be y equals 2 over 1. And so what's our horizontal asymptote going to be? 2. And so once I have this point down, I just need to find a couple of points on each side of the vertical asymptote and graph those in, and I'll know exactly what my graph is going to look like. So to do that, we would just set up our little table of points. And I would put it here in the middle, the 2x plus 1 over x minus 3. And that's going to give me my y-coordinate out. So I would pick like, we could pick a couple things. Like 0 is always easy to work with, and that's to the left of the vertical asymptote. 2 is to the left of the vertical asymptote. To the right, we could pick 4 and 6. We just need to pick a couple to get our general shape. Okay, so when I put 0 in, I'm going to have 2 times 0 plus 1. And 0 minus 3. So that's going to end up being a negative 1/3. So I'm at the point 0, negative 1/3. And then when I go for, like, say, 2, That's going to be 2 times 2 plus 1 over 2 minus 3. So for 5 over negative 1. So at 2, I'm down here at negative 5. So we can see about how this line on the left is going to go. Something like this. And then to find the line on the right, I just substitute in these two guys. So it's going to be 2 times 4 plus 1, 2 times 4 plus 1, and 2 minus 3. Or if I'm sorry, 4 minus 3. And so when I put that guy in, 2 times 4 is 8 plus 1 is 9. 4 minus 3 is 1. So when I'm at the x coordinate of 4, I'm at y coordinate of 9, which is somewhere up here. And then when I put 6 in, I have 2 times 6 plus 1 over 6 minus 3. 2 times 6 is 12 plus 1 is 13 over 3, which would be almost, it would be a little bit more than 4. It would be 4 and 1/3 or 4.3. So come out here to 6 into 4.3. And so now I can see this guy right here. And again, these lines don't cross those asymptotes. Okay, so this is how you handle a little bit more difficult one. You can always graph these on your calculator and look for some ideas and some practice. And how is this one different than 1 over x? Okay, well, it's just been moved 3 units right and 2 units up. It's been moved 3 units right. It's been moved 2 units up. 3 units right, 2 units up. So we can get those from the asymptotes. So what's the domain on this guy? The domain is going to go from negative infinity. Remember, these are x values to 3. And then from 3 to infinity. And the range is going to go from negative infinity to 2. And then from 2 to infinity. So there's your domain and your range. So just you got to practice these a little bit. There is a pattern here, and they all these graphs should look the same. Okay, they all should look like or resemble 1 over x.